Hello everyone, welcome to this tutorial. My name is Ahrari. I'm a Google Earth Engine expert. In this tutorial, I'm going to show you how to do anomaly mapping in the Google Earth Engine platform using Python API programming. So now, first of all, we need to call all necessary libraries when you want to make a bridge between Colab environment and also Earth Engine platform. First of all, import Earth Engine library like this. It is a built-in library and no need to installation first. I'm waiting for connecting to the server and then code is running and Earth Engine library connected. So in the next step, we need to call all necessary libraries when we want to deal with the satellite data. So that is necessary to deal with the satellite data. For example, the first one is X-array structure, X-array as XR. X-array is a library allowing us to convert the image collection into array structure for the array analysis. That could be very beneficial to apply machine learning algorithm. So next we need to call GeoPandas. GeoPandas is a kind of library helping us to deal with geospatial data. GeoPandas as GPD. Another library, for example, could be Matplotlib that is useful for plotting the results. Write it like this: import matplotlib.pyplot as plt. All necessary libraries imported. In the next step, we need to install XEE library. Let's go to the net and open a new page and type XEE Google Earth Engine library. The first result is a GitHub link that shows enough descriptions about the XEE capabilities and how it works and about the installation. As you can see, it is important to have the XEE next to Earth Engine and X-array structure. That's why we need to install it, because it's not a built-in library in the Python programming language, at least in the Colab environment. Pip install XEE. Let's run a code and XEE is installing. Okay. Unstable installation completed successfully. Now you can import it. Import XEE. So, all necessary libraries, all of them imported and installed. In the next step, we want to make a connection between Colab environment and Earth Engine. Earth Engine.initialize can help us to do this process. Let's call Earth Engine library and start the authentication. So, authenticate first and then Earth Engine.initialize project equals to OK. Now you need to write your project ID, the Cloud project ID connected to Google Earth Engine account. Go to the code editor environment. In the upper right here, you can see your account. Go to the project info and then copy and paste the cloud project name here, just like this. The next is OPT URL. That should be copy and paste into your code. There it is. Very simple. Let's run a code and now you will have a pop-up that shows actually permission for connecting to Earth Engine environment. Click on continue and finally connection is done. seems no problem, and in the next step we can start programming and calling our data. In the first step, I'm gonna call TerraClimate data. Go to the code editor environment and remember that through the browse data catalog you can call any other data that you prefer to work with. Here I'm gonna use soil moisture product, soil moisture variable from TerraClimate product. Just type TerraClimate to get enough information about this product. This is a monthly product available since 1958 and with monthly frequency. The image collection snippet available here. Just copy and paste it. SM is a variable name equals to the image collection. Earth Engine.image collection and select the target bands. Go to the bands and the band names listed here. So as you can see, the PR or precipitation is for example one of the bands, but here I'm gonna work with the soil moisture data. If you want to have a better view, go to the data description like this, open it up into a new page, and then you can see all the bands with the units and description and scale factors. So the soil moisture already highlighted with soil, so that select allows you to select the target band, that is the soil. In the next step, I'm gonna select a period of time in which soil moisture data is available. This data available since 1958. For example, I prefer to call the data for the last 25 years. It's totally up to you which period of time selected for your study. So, dot filter date, just like that, starting from 2000 and ends to, for example, 2024. Here it is. The period of time also imported. Let's run a code and then you can see there is a problem here. The image collection actually object has no attributes select. The select is wrong. So now the problem is solved. Okay, we have an image collection here. If you go to the variable left panel, here you can see a list of variables. Soil moisture is an image collection that usually we call it a TIFF format or consider it as a TIFF format. But here we need to convert it to a multi-dimensional array structure because this is easier to deal with the satellite data and applying algorithm. So, and also you will have higher speed of processing with the array structure. That's why the Google Earth Engine team developed XEE and to integrate Earth Engine and X-array structure for coding easier in the Python environment. So now as you can see here, we want to make a data set, a multi-dimensional data set from soil moisture. So already X are actually defined as actually it is the XR shows the X array library. From X array library, I'm gonna use open dataset to open soil moisture using Earth Engine actually engine capability. So now the data converted. Let's get a print and run it again. After a few moments, you can see the result here. Now the image collection converted to a dataset, as you can see. The dataset or soil moisture dataset is a multi-dimensional data. 3 dimension, one of them is time, one of them longitude, and another one is latitude. And also the soil moisture is the only single variable we have here. you can see the data description and the data characteristic here. So in the next step, I'm going to calculate the annual anomaly for the soil moisture in the global scale. As you can see, this product is available in global scale, and now I'm gonna first convert it uh, to the annual frequency, or aggregate it to the annual frequency by averaging technique, and then I'm gonna calculate the annual anomaly. Okay, so soil moisture annual or yearly soil moisture equals to, as the data set converted to the array structure, it is very easy to apply the data analysis method on this data set. Here we have the soil moisture data set that could be aggregated to the annual frequency using this parameter ye or y. Actually helps to convert the data based on annual formats. For each year, we want to get average, mean. In which dimension? You need to identify in which dimension the averaging going to happen. So based on time actually dimension, I'm gonna actually get the annual average. Let's run a code, and after a few moments you can see the results. And the time of processing depends on volume and frequency of input data. Higher frequency, higher spatial resolution, higher number of images causes a higher period of time for processing. But hopefully we got the result very easy. If you work with the code editor environment, you know that temporal aggregation is a little bit difficult, and you need to write couple of code lines to solve this issue. But thanks to the facilities available in the Python and X-ray structure, applying complicated algorithm is very easy. So the soil moisture annual data calculated, and now you can see the data time only available for each year: 2000, 2004, 6, 8 until 2023. Only one variable, that is soil. Okay, the annual average, it is calculated. Remember that in the data description mentioned a scale factor 0.1 that must be applied on each annual data. It is also very simple to apply zero point 0.1 as a scale factor on all data available under soil moisture, annual soil moisture. So if you check it here, you can see the range of values is around 500 for a part of the world, but you can apply the scale factor to rescale the values into the correct range. Let's run a soil moisture annual again to apply the scale factor on soil moisture data. Once the process completed, you can check it out, the new annual soil moisture that is created. Hopefully there is no problem in the processing and it's ongoing. Now annual soil moisture calculated, and you can see 500 reduced to 50 because it is already multiplied to the scale factor suggested by Google in the data description page. Okay, now the annual data is ready, and I'm gonna actually get a long-term average for 25 years and then subtract each year from the average. It is also very simple. For example, imagine that here the annual average or soil moisture average equals to get annual soil moisture and calculate the average based on time dimension. Let's run a code, and as you can see, the average soil moisture calculated. SM mean, let's get a print. After a few moments, a two-dimensional data created. Why two-dimension? Because the time is over and we got a single image for the whole period of time. This is not multi-temporal anymore. Only latitude and longitude is available for this product. Okay, let's make a visualization or make a visual uh, view from the uh, long-term average. So now through the SM mean, select the target variable that is soil, then plot it using plot function. We need to identify longitude and latitude or define the latitude and longitude here. X equals to longitude, y equals to latitude. The color map equals to jet or any other color palette you prefer. Let's run a code and see the results. Here it is, the actually 25 years average from soil moisture data. You can change the dimension. The fixed size allows you to change the image dimension. For example, 7 and 4, like this. Now it has a better shape, and also you can change the rate of the value. It seems that most of the values are lower than 100 millimeter. So we can rearrange the output, we can visualize the output to have focus on the values changing from 0 to 100. So here it is, you can change the minimum value to 0 or 10 even, and Vmax, the maximum value equals to 100. After a few moments, a new map is created that shows soil moisture variation, so from 10 millimeter to 100 millimeter. So, and this actually arrow shows that still there are some values above 100 millimeter, and you can see them with the dark red region. And also another arrow downside shows still there are some values less than 10 that could be very useful for the image interpretation. So imagine that you want to get export from this image. PLT, unlike the code editor environment, in the Python environment you can produce very interesting layouts and get the output easily. plt.savefig. I'm gonna save soil moisture average with PNG format. DPI equals to, for example, 360, higher DPI, higher quality, and vice versa. Let's run a code again, and after a few moments, go to the left panel, and here soil moisture mean is available. Click on download and go to download and click on save. There it is. And now as you can see, the soil moisture image with a global scale and 5 kilometer spatial resolution created. So back to the code. In the next step, I'm gonna show you how to calculate the anomaly. Actually, I'm gonna calculate the differences between each year compared to the long-term average. So the anomaly image equals to, okay, go to the dataset variable, and now here you can see we have one variable SM mean that shows the long-term average, and SM annual shows the annual soil moisture values. Let's get subtract them from each other. Soil moisture annual minus or subtracted from soil moisture mean. Let's run a code and anomaly dataset created. As you can see, the anomaly dataset, let's get a print. The anomaly dataset has 3 dimensions: lat, long, and time. For each year, the anomaly calculated. So let's plot one of the anomaly images. For example, I'm gonna see how much soil moisture, for example, in 2020 deviates from the long-term average with a spatial distribution. So now I'm gonna show you how to filter the data based on date and based on the region of interest. For example, I'm gonna have focus for this part of the world, and I want to get rid of the rest of the world. So, and I'm gonna see the result for 2020. Let's get a subset from data. The annual anomaly already created. The cell here is a function that allows you to make a spatial and temporal subset. Okay, the target latitude equals to, for example, let's start with longitude first, equals to, a slice allows you to select uh, start value and end value for the longitude. For example, from 0 to 180 for the right side, this way, from 0 to 180, and latitude equals to a slice from 0 to 90. So, and in the next step, another dimension is time. Time equals to, I'm gonna select a date. Here, for example, 2020, December 31, 2020 selected. Let's run the sub image and plot it. So, sub.plot. Here, the sub included one variable that is soil, and plot needs defining the latitude and longitude. X equals to longitude, y equals to latitude, and also the CMAP, again like jet, and fixed size equals to, for example, 7 and 4. Let's run a code here. You can see we have a spatial subset that works very well, but most of the value ranges between -10 or +10. Let's make a better visualization. -10 Vmax equals to +10. Let's run a code again, and here, as you can see, now the variations of soil moisture value highlighted much better, and now you can discriminate variations much easier. So as you can see here, the red region, or some green to red, actually shows some region in which, for example, the green values close to 0 shows the region in which soil moisture doesn't change or didn't change a lot, but the yellow and red region shows the soil moisture in these areas is higher than the long-term average in 2020. And also the blue region shows the soil moisture is less than long-term average in the Russia and also some of the European countries. It is also possible to add the actually border of global countries that allows you to have a better interpretation about the results. Okay, go to the file and let's download the global generalized layer, global generalized countries, world countries generalized from ArcGIS Hub. This link is available below the video in description box and you can find it. Let's go to the link, and here you can download the dataset. Let me to make it a little bit bigger. I don't know why yes, here we have a download option. Go to the download, and as you can see here, different format is available. Just click on download to download the generalized shapefile for the whole of the world. Okay, I did this process previously, and once the data downloaded, you can upload it into this environment. For example, now as you can see here, let me to check it now. Seems it is not downloaded on my system, or it might be Word. Yes, Word countries generalized already available. Different systematic files are available. You need SHP, SHX, DBF, and PRJ. Let's import it or upload it first. You can see it is uploading. Once the all files uploaded here, now you can import it into the code through the GeoPandas. So a new variable as shp created equals to from GeoPandas read file allows you to enter the address of shapefile. So you copy and paste it. It is shp inserted into the code. You can get a preview from the content, but it is very important to check the CRS or coordinate system for the input. As you can see, the coordinate system is EPSG 3857. That's not gonna work to overlap between a vector and raster layer. Originally, remote sensing data from Earth Engine actually has WGS84 as a coordinate system. Now we need to reproject this dataset into WGS84. So SHP or countries equals to shp.2crs. Let's enter the target coordinate system, EPSG 4326. This is the WGS84 code you can use for whole of the world instead of 3857. Let's run a code again and check the countries coordinate system. Run the code EPSG 4326. Okay, now the data is ready and we can visualize the output. But you need to make a little change for the plotting process. So define two variables as fig and x equals to from PLT make a subplot structure, subplot like this, and then you can enter the fig size in there. Remove, cut, and paste it. Okay. And in the next step, we need to actually make a connection, make a link between the current plot and the base plot or frame plot. So x equals to x, the axis equals to main axis created. Okay, nothing changed, but it is necessary for plotting another layer on the current raster layer. Okay, The next layer is the countries CRS. Countries, just like this. Countries dot boundary. Dot boundary dot plot. Just like that. Now let's run a code. Nothing happened, but now we have another plot that shows the country's border. The problem is about the axis. The axis for the first and second plot must be same. Let's run a code again, and now you can see the actually overlapping between vector and raster layer. You can change the color and also change the line width. For example, line width equals to 1 and border colors changed to black, just like this. Very easy to do. Now in the next step, even you can also try with different colors, such as cool warm. There are various actually color palettes that you can try with them and get a better understanding to make a better visualization for the output. Now you can see the low moisture values with the red and higher moisture values with the blue color. Very easy. And also you can change the dimension easily to make the actually legend and frame with the same or match size. For example, let's change the figure size value. No, it's not better. Yes. And now the figure size is very good, and also the legend size and image size, both of them are very clear. Let's get the output plt.savefig. The output image is soil moisture anomaly with PNG format. Set the DPI equals to 360 to have a higher quality. Let's run a code, and after a few moments, soil moisture anomaly is ready to use. There it is. Now as you can see, we called the satellite data and we did the anomaly detection with a good accuracy through the satellite data in Python programming language. I hope you liked this tutorial as much as I did. If you had any question or problem regarding this tutorial, you can find the code link below this video on my YouTube channel and you can check it out with your codes. If the problem still exists, you can reach me out on my YouTube channel. Thank you for your attention.